Cones. So a cone can be thought of as a circular pyramid. So in the same way that a cylinder is not technically a prism, it behaves in all the same ways. A cone is not technically a pyramid, but again, it behaves in all the same ways. So the volume of a cone is going to be 1/3 times the volume of the corresponding cylinder. So that is 1/3 times pi times r squared times h. So here we wish to find the volume of the cone pictured opposite, giving our answer firstly exactly and then rounding it to 2 decimal places. So the volume is going to be 1/3 times the volume of the cylinder, which is pi r squared times h. And so we have 1/3 times pi times, in this case the radius is 5, so 5 squared, times the height, which is 12. Again, you want to use that third easily, so rather than trying to do 25 over 3, let's do 12 over 3, which is 4. So we have 4 times 25 pi, which means we have 100 pi. So the volume is exactly 100 pi centimetres cubed. To 2 decimal places, that's going to be 314.16 centimetres cubed. Okay, so surface area of a cone is quite a bit more complex. So if we unfold a cone, we have a circle on the bottom, that's pretty straightforward, and then we're going to have a shape which is actually the sector of a circle. So if you were to take those two radii and join them together, you'll create a cone. You imagine creating a witch's hat as a kid. So the defining dimensions of the cone are the radius and the height. Now, another measure that we're going to need to make use of in finding the surface area is also going to be this, what we call the slant height. I'm going to call it S. Some formulas use a lowercase l. So we're going to need to know that as well, because if we think about the sector that we've just unfurled, it will be that slant height that forms the radius of that sector. So this length here will be S. So we've got the circle, which is just simply, and it has a radius of r. So the area of that piece is pi r squared. Now, it's this sector that's more complicated. So, like any sector, we want to imagine that it is part of a bigger circle. So it is part of a circle with a radius of s, the slant height. So it's confusing here because there's more than one circle going on within this problem. The circle on the base, which has a radius of r, but then the sector, which is part of a larger circle, which has a radius of s. Okay, so when we're trying to find the area of a sector, we usually need to be able to think about what fraction of the circle this sector makes up. And sometimes we'll be given information about the angle at the centre. So for example, we might know that this angle in here is, I don't know, 150 degrees, and we know that that then tells us that the fraction that that sector makes up is 150 out of the total 360 degrees in the circle. Now we don't know anything about the angles, but we do actually know something about the arc lengths. So an arc is part of the circumference of the circle, so what I'm talking about here is this length around here. And again, if we imagine going back to our original cone, that length, that arc length, corresponds to the circumference of that circle, of that small circle. So that means that this length here is 2 pi r, the circumference of the circle with a radius of r. Now, we know that the total circumference, the whole way around here, this is a circle with a radius of s. So that total circumference is 2 pi s. So now, if we're thinking about the area of this sector, we now have information to give us the fraction, what proportion of this total circle that this sector takes up. And that is that it is 2 pi r out of a possible 2 pi s. So rather than looking at the ratio of the angles, we're looking at the ratio of the arc lengths. And then that is the fraction of the area of the total circle, and this is a circle with a radius of s, so pi s squared. So looking at this, so that's the area of this sector, The 2 pi's cancel out. We've got r over s times pi s squared. So that will be pi r s squared over s. So one of those s's on the numerator will cancel with the s on the denominator, and we have pi r s. And so we find that our total surface area, oh, I've written all over there, our total surface area, let me pop that up there, is going to be the area of the circle on the base, which is pi r squared, plus the curved surface, which is pi r s. Sometimes you might see this formula with the pi r's factored out, but it's completely unnecessary to use that. So pi r squared plus pi rs, and again, like the formula for the surface area of a cylinder, it's important that you understand where those pieces of the formula have come from, in case you have a cone without a base, so a party hat you're trying to work out the surface area of. So you're able to break up this formula into its composite parts as necessary. Okay, so let's have a look at a simple example. Here's a cone, diameter of 10, which means a radius of 5, a height of 12. Now remember, we also are going to need the slant height if we are going to find the surface area. So we know that that length there is 12. We're going to need this length here, the slant height. I apologise for having a 5 and an s in the same problem. So Pythagoras again, s squared is 12 squared plus 5 squared, which is 144 plus 25. And again, if we knew our Pythagorean triads here, we would have been able to get to this answer more quickly. So s is 13. 5, 12, 13 is a triad. So the slant height here is 13. So our surface area is going to be the circle on the bottom, which is pi times r squared, so in this case pi times 5 squared, plus the curved surface, which is pi rs, so pi times 5 times s, which is 13. So we have 25 pi plus 13 fives are 65 pi. So adding those together gives us an exact surface area of 90 pi centimetres squared, which is approximately equal to 282.74 centimetres squared. Okay, in this third example I should say, again, it is a dimension that's unknown and we're given the volume. So it's a cone and we're given the volume, so I'm going to need to make use of the equation for the volume of a cone, which is 1/3 times the area of the cylinder, which is pi r squared h. So I know the volume, it is 54 pi. I know the radius, it's 3, and it is the height that's unknown. So we want to solve this equation for h. So we have 54 pi equals 1/3 times pi times 3 squared, so that is 1/3 times 9 pi, which means 54 pi equals 3 pi times h. I want to divide both sides by h. Divide both sides by 3 pi. The pi's will cancel out. 54 divided by 3, 3 goes into 30 10 times and into 24 8 times, so that is 18. It's a height and my units are centimetres, so 18 centimetres is the height of this cone. Now actually, I got a bit ahead of myself there. The question asks me to find the area of the curved surface of the cone. Okay, so let's think about what we've just worked out. So we have a cone. Now we knew its volume and we knew its radius. Its radius was 3. And we've just worked out its height to be 18. And so now that we know the radius and the height, we should be able to work out s, which will allow us to work out the curved surface. So s squared is 18 squared plus 3 squared. 18 squared is 324 plus 9. So that means 333. So s is the square root of 333, which if we simplify our surds, it's a bit of a complicated one, but 333 is 9 times 37, so this is 3 root 37. My curved surface is pi rs, not pi r squared, habit, pi rs, which is pi times 3 root 37, or 9 root 37 times pi, which is approximately 171.99. What are our units here? That's an area, and we're in centimetres, so centimetres squared. Apologies that things got a little bit cramped there. So we only needed the answer to 2 decimal places, but exactly it is 9 root 37 times pi. So cone surface area is pi r squared plus pi rs, where the pi r squared is the circle on the bottom and the pi rs is the curved surface, and the volume of a cone is 1/3 times the area of the corresponding cylinder, that is 1/3 times pi r squared h.